Welcome viewers, welcome back to this course. So, today we are going to start with a new topic, because in the previous classes we have all developed the technique to solve the differential equations. Basically till now we have solved the second order linear differential equation, homogeneous, non-homogeneous, with initial condition or the boundary condition. So, today we are going to start with a new topic, and that topic is also used to solve the differential equation. So, today we are going to start with the lecture 14. So, now as I told you that we know that I have a differential equation, it may be a initial value problem or the boundary value problem, and on the other side I have a algebraic equation. This is the algebraic equation, and I ask that which one is easier to solve. If you have a differential equation on the one side, on the one hand, and algebraic equation on the other hand, and you want to solve, which one is the easier to solve. So, obviously the answer will be that algebraic equation will be easier to solve. So, today in the topic we are going to transfer this differential equation, generally the initial value problem, into the algebraic equation, and then we will solve that one. So, how? Because I have a differential equation and I am converting this differential equation into the algebraic equation by transform something using some transformation. So, obviously that transformation should contain the sign of integral, because the anti-differentiation is the integration. So, from here I will start with a new topic, and that is the Laplace transformation. So, for the Laplace transformation I define that let I take a function f t. So, now we are defining the function in terms of t, that let f t be a function well defined on the interval 0 to infinity, then I take the Laplace L of f t by taking the integration from 0 to infinity. Here I am taking a new variable e raised to power minus s t, and then multiply by f t dt. So, this is the integration we are going to take. Now, if this integration is finite, so if this integration, this one is finite value, then we say that this integration exists, and in that sense I will say that the function f t has the Laplace transformation. And if you see from here that we are doing the integration with respect to t and then putting the limit. So, after doing all this calculation, you will see that I will get the function on the right hand side in the form of s. So, I call it this one as a function of s, and then I am taking the Laplace of small f t, then we generally represent this one by the capital S. So, f is a function of s, and from here I can say that this f is a Laplace transformation of this small f t. Now, so let us take few example to understand more that how this integration happens. So, suppose I start with the very simple example. So, take some examples. Let us I take a function, my f t is equal to some constant function 1. This is the simplest function I can define. So, f t is equal to 1. and t belongs to 0 to infinity. Now, I want to take the Laplace of this one. So, the Laplace of my f t in this case will be integration from 0 to infinity e minus s t into 1 dt. So, from here I can solve this integration, and the integration of exponential will be e minus s t divided by minus s, and now putting the limit from 0 to infinity. So, this one I can define as, so 1 over minus s I can take common, then I put the limit t tends to infinity e raised to power minus s t minus, and putting t equal to 0. So, it will be E 0. So, from here I can define that this is minus 1 over s, and now this limit I want to find out. So, in this case if you see exponential e is a minus s t. So, t is my always positive value starting from 0 till infinity. So, in this case it depends upon that what is my s. So, if you see that if I take, so this one I will just define now limit t tends to infinity e minus s t, it will be minus 1. So, now I take for s, if I take s less than 0. So, in that case I am choosing my s to be negative. So, if s is negative, then you can see from here, if s is negative, then this will be a positive value, and in that case if I put the limit t tends to infinity, then in that case I will say that my Laplace of f t is equal to 1 will be infinity, or even I am taking s equal to 0 also. So, this is the case. Now, what about if I take s positive? So, if I take s positive, then for the limit if s is positive, then this one I can write as minus 1 over s limit t tends to infinity. I can put this one as 1 over e s t minus 1, and then this is positive value, the s is positive, t is positive, this will be going to be infinity, and from here if you see, then this will be minus 1 over s, and this value will be 0 minus 1. So, from here this value will be 1 over s. So, from here I can write that the Laplace of f t is equal to 1, this will be 1 over s if s is greater than 0 and it is infinity when s is less than equal to 0. So, that is the Laplace transformation for function f t is equal to 1. So, the same example I can take. So, let us take another example. I take the another example. So, let us take another example. I choose f t is equal to some polynomial t. So, what will happen in this case? I want to define the Laplace of f t is equal to t. So, this one I can write as a f s. So, it is my 0 to infinity e raised to power minus s t into t dt. So, here I have to take the by parts rule to find out the integration, because in the Laplace transformation always you need to find out you will get the function of this type, and then you have to apply the integration by parts. So, in this case what I will do, I will take t as a first function integration of and then putting the limit minus 0 to infinity, and here I will take the derivative t, that is 1. So, it will be e raised to power minus s t dt by minus s. So, integration of the second function. So, that gives me, again it gives me, now from here I will get minus 1 by s, I will take common, and here I will put the limit t tends to infinity t e raised to power minus s t minus, and I am putting 0. So, it will be 0, and this minus s I can take outside. So, this will be plus 1 by s 0 to infinity e raised to power minus s t dt, and you know that this is the Laplace transformation of the function 1. So, this one we have just done, finished this one. So, this is a Laplace transformation of this one, and that value is 1 by s. So, from here I just define 1 by s, and then solving this integral this limit. So, I will take the same two cases. So, let us take the case when s is positive, s is greater than 0. So, in that case this will be limit t tends to infinity t by e raised to power s t plus, so here 1 by s, and this will come 1 by s. So, I can take it as s square, okay, because I am choosing that s is positive, s is greater than 0. So, in that case what will happen, I will get infinity by infinity form, and then by the L'Hospital rule, from the L'Hospital rule I will get the limit t tends to infinity 1 over s e s t, the derivative, plus 1 by s square, and then I am putting that limit t tends to infinity becomes infinity, and then 1 by infinity will be 0. So, from here I will get my s square when s is positive, and similarly if I take s negative, then its value will be negative infinity. So, this will be equal to 0. So, from here I can say that my f s will be of this type, and infinity when s is less than 0. So, this is the Laplace transformation of the function f t, and if you see that if I take the Laplace transformation of t square and doing the same thing again, what you will get, I will getting the from the by parts integration, from this place I will get t into e raised to power minus s t, and that is the Laplace of the t just we have done. So, the same way we can do. Now, suppose I take the Laplace of f t is equal to t square. So, the same thing will work here. So, now my Laplace of t square will be 0 to infinity t square e raised to power minus s t dt, just now do that. So, it is a t square e raised to power minus s t by minus s 0 to infinity. So, this will be becoming 0 minus, then I will take the integration and it will be 2t, and then e raised to power minus s t over minus s dt. So, this part will be 0 again by putting the limit for s positive, and in that case I can say that this is going to be 0 and this will be. So, we are getting here 0 this value, and minus plus sign will be here, and 2 will be taken common. So, it will be 2 by s, and then inside I will get infinity t e raised to power minus s t dt, and this is the Laplace of the function t that we have just found, that 1 over s square. So, from here I will say that the value of this will be s cube when s is positive and infinite when s is negative. So, from here I can define my Laplace for the general function. So, now if I have a f t is equal to t raised to power n, then I can define from here that the Laplace of f t is equal to t raised to power n. So, here I am getting 2. If I take the t cube, so I will get from taking the derivative, so that will be 3 t square and then this value. So, again the same thing, so 3 will come. So, here it is 2 by s cube, there it will come 3 into 2, so 6. So, from here I can say that it will be s n plus 1, because when I am taking t square, the s cube is coming. So, n plus 1 t square 2. So, from here I can say that n factorial. So, 2 is a 2 factorial and then it will be multiplied by 3. So, it will be 6. So, 3 factorial and so on. So, from here I can define my Laplace for any polynomial of degree n, and its Laplace transformation will be n factorial by s n plus 1. So, this is the simplest function, we have taken the Laplace transformation. Then I can define the Laplace transformation for any other function. So, let us take another example, and I take the function f t is equal to some exponential function e raised to power a t. So, this function we are defining, and this function is well defined for t belongs to 0 to infinity. And then in that case, if I want to define the Laplace of e a t, so it will be 0 to infinity e minus s t e a t dt, where a is a real number. So, from here I can define from this e raised to power minus s minus a t dt and this will be minus s minus a t over minus s minus a, and then putting the limit 0 to infinity. So, from here I can say that I just take the common s minus a and then putting the limit. So, it is the limit t tends to infinity e raised to power minus s minus a t, and then putting the value 0 here. So, minus it will be e 0. Now, the same case will happen. So, now I will choose that my s minus a is positive value. So, in that case I can say that this will be 1 over s minus a, and if I choosing my s minus a is a positive value, then this will become 0. So, this will be 0 minus 1, and from here I can write it as a s minus a. So, from here if I will say that this is equal to 1 over s minus a when s minus a is positive, or I can say that s is greater than a, and this will be infinity when s is less than equal to a. So, from here I am able to find the Laplace transformation of any exponential function. Then, so this is that we are able to find the Laplace transformation of any polynomial or the exponential. Now, I want to define one property of the Laplace transformation. So, if you see that the Laplace transformation of a function f t, where f t is a well defined function in the interval from 0 to infinity. So, this is 0 to infinity e raised to power minus s t f t dt. So, from here I give a property 1 of the Laplace transformation, that Laplace transformation is linear. So, what is the meaning of that? The meaning of that is that a transformation is said to be linear if I want to take the Laplace of C1 f1 t plus C2 f2 t. So, this is the linear combination of the two function. So, if this comes equal to C1 and the Laplace transformation f t plus C2 the Laplace transformation of f2 t, then we say that the Laplace transformation is a linear function. And now you know that in the Laplace transformation we are dealing with the integration, and the integration itself is a linear transformation. So, from here if I just want to find out what is the Laplace transformation of this linear combination of two functions where C1 and C2 are the constants. So, this will be becoming 0 to infinity, and this is e raised to power minus st. So, C1 f1 t C2 f2 t dt. So, from here I can write that just separating the things separating the things, because this integration I just separate this one as C1 I can take outside, and then I can apply e raised to power minus ft dt plus C2 0 to infinity. So, this is my f1 and this will be f2 t dt, and then from here you can see that this is the Laplace transformation of f1 t and this is the Laplace transformation of f2 t, and then I can write this one as C1 the Laplace transformation of f1 t plus C2 the Laplace transformation of f2 t, and then from here I can say that Laplace transformation is a linear transformation. Now, one more thing I want to just define. So, let us we have taken the Laplace transformation of the function and the exponential. So, I just now I want to take the Laplace transformation of any trigonometric function. So, I just want to define that what is the Laplace of a function f t is equal to cos a t, or what is the Laplace transformation of a sin a t. So, this one I want to find. So, now this one we can define like this one. So, I just want to find the Laplace of cos a t plus iota is the complex number, sin a t. So, this one I want to define. So, just now I told that the Laplace transformation is a linear transformation. From here I can define that cos a t plus I sin a t, I know that it can be written as e a I t, this is the exponential function, and this one I can just write 0 to infinity e raised to power minus st e a I t dt, and I know that the Laplace transformation of a exponential function is equal to, so this is I already know that this is equal to 1 over s minus a I when s is greater than a I. So, it is 0, and this is infinity when s is less than equal to 0, because a I is just the imaginary number. So, from here I can write down the Laplace of cos a t plus I sin a t is equal to, so this one is I will separate this complex number into the real part, the imaginary part. So, I just multiply by s plus a I and divide by s plus a I. So, from here I can write that s plus a I and dividing by s plus ai. So, that will give me s square plus a square when s is positive. So, from here I can write this function in the simplest form, and I can separate this one as a real part. So, real part is s over s square plus a square, and then I can write iota a over s square plus a square when s is positive. Now, comparing the real part and the imaginary part. So, from here I can say that the Laplace of cos a t is taking the real part to equal. So, this will be s over s square plus a square, and the Laplace transformation of sin a t will be a over s square plus a square. So, this one we are able to find. So, if somebody asks that what is the Laplace transformation of cos 2t, so this will be s over s square plus 4. What is the Laplace transformation of sin 2t? So, this will be 2 over s square plus 4. Now, if somebody asks that my fs is 4 by s square plus 9, then which function f t we can find such that the Laplace of that function is equal to this function. So, basically I want to find what is the Laplace, what is this function f t such that this is equal to my fs. So, in this case we can just say from here that I want to define the function f t such that the Laplace inverse of fs is this one. So, from here I will define, so from here I can say that I can define a Laplace inverse such that if I take the inverse of fs, then I should get the function f t. So, from here we define another type of way finding the inverse, and that we represent by f L inverse. So, from here now my fs is 4 by s square plus 9, and I know that if I have my Laplace of sin 3t, then it should be 3 by s square plus 4, s square plus 9. So, from here I can say that 4 cross 3 divided by 3, and then I will write s square plus 9. So, from here I can write that this is equal to 4 by 3 by s square plus 9, and I want to take the inverse of fs. So, this will be L inverse 4 by 3 9, and this one I can take common. So, I want L inverse 3 over s square plus 9. So, if I define this one, so this will be equal to 4 by 3, and then this is Laplace of sin 3t. So, from here I get the solution, and that solution gives me. So, from here I can write that the Laplace transformation of 4 by 3 sin 3t is equal to 4 by s square plus 9. So, now we are able to define the Laplace transformation of trigonometric function also. So, let us define another function, because from till now it seems that we are able to take the Laplace transformation of any function. It may be a polynomial, it may be a trigonometric function, it may be a exponential function. So, let us take the Laplace transformation of the function. So, let us take another function f t, it is 1 by t. So, let us take this function 1 by t. So, in that case, and you know that my t belongs to 0 to infinity. So, this function has some that at t equal to 0, this function is value is infinite. So, this function is undefined at the value t equal to 0, but we are dealing with the integration. So, let us take that, try to find the Laplace of f t is equal to 1 by t. So, if you take the Laplace transformation of this one, I can define this integration from 0 to infinity t dt, and in this case you will see from here that this function, if I want to take the integration and taking this 1 by t as my first function and e raised to power minus s t as the second function that we are doing, then if I take the derivative. So, let us do this one, I go by the same way. So, let us take 1 by t as a first function and e raised to power minus s t over minus s as the second function, 0 to infinity. So, what is the differentiation of 1 by t? So, it will be minus 1 by t square, and then it will be minus s t over minus s dt. So, this will keep increasing like this one, next will be minus 1 2 over t cube and so on, and here also I am dividing by t. So, if I take that as we are taking s is positive, so in that say, so if I just take the integration of this function, for infinity it is okay, but when I take t equal to 0, then it has become infinity. So, in that case I can say that for this type of function, this Laplace transformation does not exist. Or I can take the another function f t is equal to e raised to power e t, or I just take the function another function t raised to power t. So, like this function, if I just take the Laplace transformation, you can see that the Laplace transformation does not exist. So, for this one we just want to find out that which functions we are able to take the Laplace transformation, and then we get into the existence of the Laplace transformation. Laplace transformation. So, before going to the existence of the Laplace transformation, we want to define two terms. The first terms we want to define, and that we already know in fact, is that the first one is that what do you mean by a function f t is piecewise. Piecewise continuous in the interval 0 to infinity. So, what do you meaning by the piecewise continuous in the interval 0 to infinity? It means that my function, so let us define one function. So, this function means that this function is continuous, but in the pieces in the whole interval from 0 to infinity. Like suppose I have some function, this is my t axis and this is my f t. So, I define a function that from 0 it is value is this one, from this value here. So, this is t1 I say, and after that the value of the function is this one, and then this call it at t2, and after that the value of the function is like this one for all value of t. So, in this case I know that my value of the function at t equal to 0 is this value, because we are discussing here that my function is a continuous function, but in the pieces. So, if the function is a continuous, it means its value is well defined at every value, at for any value of the t. So, at t equal to 0, so this is my t equal to 0, the value of the function this one. So, let at t equal to 1, the value of the function is this one, and starting from this, that at t equal to 2, the value of the function is, let us take this value as a function of the value, and then this one. So, from here I can say that my function f t is this function. So, it call it as f1t, f1t when t is defining 0 to t1. So, at t1 also I am taking this value. So, let us take equal to sign here. Then I will take my function f2t. So, f2t is, so t is greater than t1 and less than equal to t2, because t2 value is this one, and then I have taken f3t. So, t is greater than t2 up to infinity. So, in this case my function f t is in the pieces, but this is continuous function, and in fact if you see from here, it has a discontinuity at the point this one, and which is we generally take as a jump discontinuity. So, we can say that my function f t in this case is a piecewise function with finite number of jump discontinuity. Now, you know that in the Laplace transformation we are dealing with the integration, and for the integration even the function has a jump discontinuity, we are able to take the integration. So, suppose this function I want to take the Laplace transformation of this function f t. So, it will be 0 to infinity e raised to power minus f s t f t dt. So, because of the properties of the integration, I can split this integration from 0 to t1. So, this will be e raised to power minus s t f1 t dt plus t1 to t2, it will be f2 t dt plus t2 to infinity, it will be f3 t dt. So, in fact, I am able to define the Laplace transformation for any piecewise continuous function which has the jump discontinuity, and that is of finite in numbers. So, this is the one of the properties is there, and the second one I will define, the term I will define, and that is called the function f t is of exponential order, and that exponential order alpha. So, what is the meaning of this? So, this is called that if I am able to write my function f t, so this is my function f t, suppose the value of this is always less than some constant m e raised to power alpha t for all t infinity, or sometime we are unable to take this. So, my alpha, you can say that m and alpha are real number and positive. So, in this case I can say that this function has a bound, that bound is by m e raised to power alpha t, and t we are defining this one. So, sometime we are also able to write this one for t greater than equal to some capital T, because it may happen like, for example, so let my f t is there. Now, exponential. So, let us take alpha is equal to 1. So, e raised to power t. So, at t equal to 0 its value should be 1. So, suppose this is my exponential function e raised to power t, and I have my f t of this type. So, this at this value its value like, so it is value like this one, then this one, then this one, then after some time its value is always less than et. So, in that case this is the point. So, I just take a derive this function again. So, my function like this one, and then after this value. So, from here I just choose the value of this one, and this one I call it capital T. So, from here you can see that my function is always below the function e raised to power t. So, from here for this function I can say that my function f t is less than equal to m, I just take 1 and alpha I will take 1. So, it is always less than t for t is greater than equal to capital T. So, sometime we are able to find this capital T also. So, what is the meaning of this? It means that whatever the function I have, and if I take the positive value, the modulus value of that function, so that is always less than equal to some number m e raised to power alpha t, means e raised to power alpha t is an exponential function. So, my function should lie below this exponential function. Like suppose I take my f t is equal to 1. So, in that case I can say that my 1 is always less than, just I take 1, m is 1 and alpha is 1. So, I can take E t, and I also know that my function is 1 here, this is my f t, and the exponential function is like this one. So, for all value of t, this my function f t is always below the exponential function. So, this function f t is equal to 1 is of exponential order 1, or I can take my f t is equal to t. So, in that case I have the function that is this one, and this function is always below the exponential e t, or I can choose my function sin t, cos t, and its value is always 1, maximum value is 1. So, it is always less than this one. So, from here I can say that my exponential function like this one, and this is a value, the maximum value is 1, and my exponential function is going from here. So, this is my e raised to power t, and this is my function sin t. Similarly, I can take cos t. So, this function is always less than this one. So, I can say that my function sin t is of exponential order 1. So, let us define one. Now, I will define that what existence. So, what is the, so in this case I will say that if my function f t is piecewise continuous and of exponential order alpha, then its Laplace transformation exists for all S sufficiently large. As we have seen that in the Laplace transformation, we have taken the different value of s. When s was positive, the Laplace transformation was valid. When s was less than or equal to 0, it was infinity. So that is the value of s we are talking about. And specifically, if ft is, so from here I can say that if ft is piecewise continuous, then and exponential order, then ft will be is m e raised to power alpha t for t is then Laplace transformation exists. So, if my function f t is piecewise continuous and of the exponential order alpha, then its Laplace transform exists for all s sufficiently large. So, this one is there. The proof is, so I just want to take the proof of that function or that existence theorem. You can just say that this is the existence theorem. So, the proof, so for the proof, now if you see that here exponential order function means that the modulus of the function should be bounded by this factor m e raised to power alpha t. So, now I will take the help of, because here we are dealing with the Laplace transformation and that is the integration, and integration you can say that this is the extension of the summation, and as we were doing in the case of series solution, and we know that the absolute convergence of the series is equal to the convergence of the series. So, from here I know one thing is that my integration from 0 to infinity e raised to power minus st f t dt, this is always less than equal to f t dt modulus value, because if my exponential function is always positive, my function f t is also positive, so in that case I will get this equal sign. If it is a negative, then it is a less than, and from here I know that this can be written as 0 to infinity, it is always positive. So, I can write from here, I am just taking the modulus value inside the integral, and this value I can write down as, so this is less than this one, and this is given to me that this is equal to 0 to infinity e raised to power minus st, and this value is given to me that function is exponential order. So, my modulus value of f t is less than equal to m e raised to power alpha t. So, I can take m outside here, and this will be e alpha t dt. So, from here I will get the value m e raised to power e minus s minus alpha t dt. So, from here this is, I know that this is equal to 1 over s minus alpha when s is greater than alpha, and infinite when s is less than equal to alpha. So, from here I can say that the Laplace transformation of the function f t, which is either a piecewise continuous function or the exponential order, exists, and this is equal to 1 over s minus alpha when s is greater than alpha, and infinite when s is less than equal to alpha. So, that is the existence of the Laplace transformation of the function f t. And from this one I can say that one thing is also I can observe from here, that if I choose, so this is equal to f s, okay, and s is greater than alpha, alpha is any number, positive number. So, in that case my s is always greater than that positive number. So, from here I can say that what will happen if I take limit s tends to infinity Fs in this case, because this is we have done for any general function. So, what will happen, we will take the limit s tends to infinity Fs. So, from here you can see that the alpha is some number, real number. So, from here I just take limit s tends to infinity, it means we are dealing with this function value of the function. So, this is s minus alpha, and from here I can say that this value. So, from here I can write down the another property of the Laplace transformation is that if I take s tends to infinity limit putting on the Fs, that value is always equal to 0. So, this is the another observation we should keep in mind about the Laplace transformation. So, in this class we have just started with the Laplace transformation, and then we have discussed that the existence of the Laplace transformation. In the next class we are going further from this one. So, thanks for watching.